In this video, we're going to talk about the pKa values of acids. If you're studying for your first semester of organic chemistry and you're preparing for the first exam, likely you're going to be tested on acids and bases. And to really know if one acid is stronger than another, it really helps to know the pKa values. And that's what we're going to do today. We're going to go over a ton of pKa values. So if you have your notes, you may want to write this down. First, let's focus on the periodic table. On the periodic table, we have elements like carbon, nitrogen, oxygen, fluorine, and below that, chlorine, bromine, and iodine. You need to know that acid strength increases as you go to the right. And the reason for that is due to electronegativity. Acid strength also increases as you go down, and the reason for that is due to atomic size. And this is for binary acids. This is when hydrogen is directly attached to the element. So to give you some examples, we have methane, ammonia, water, and HF, hydrofluoric acid. A typical alkane has a pKa around 50 to 60. The ammonia hydrogen has a pKa of around 36. For water, it's 15.7. For HF, hydrofluoric acid, it's 3.2. Now, the molecule with the lower pKa is the stronger acid. So HF is a stronger acid than water because it has a lower pKa value. So as the pKa value decreases, acid strength increases. So make sure you understand that. Low pKa values correspond to a stronger acid. Oh, by the way, as the pKa values go down, the Ka values go up, which is directly related to acid strength. Now, below HF, we have HCl, HBr, and HI. HCl has a pKa of around -7. HBr, it's like between -8 and -9. And HI is between -9 to -10. Now, notice the difference in values between HF and HCl, HBr, and HI. By normal standards, HF is considered a weak acid. Water is considered neutral. So we can see the difference in pKa values here. But these acids, HCl, HBr, and HI, they're considered strong acids. And strong acids typically have a pKa in the negative range. So if the pKa is like -1, -2, -3, you're dealing with a strong acid. Just keep that in mind. Now, because HF is a stronger acid than water, that means that the conjugate base of HF, fluoride, is a weaker base than the conjugate base of water, which is hydroxide. So remember, the stronger acid has the weaker conjugate base. The weaker acid has the stronger conjugate base. So why is fluoride weaker than hydroxide? The weaker base is the more stable compound. The stronger base is the less stable compound. So fluoride is more stable than hydroxide. And the reason is due to electronegativity. Is it better to put a negative charge on the more electronegative atom or the less electronegative atom? The answer is the more electronegative atom. Fluorine is more electronegative than oxygen. As a result, it can handle the negative charge better than oxygen can. So that's why acid strength increases towards the right. It's due to the increase in electronegativity of the elements as you go from left to right. Now, as we go down, atomic size plays a role. So HI is a stronger acid than HF. That means that iodide is a weaker base than F minus. Now fluoride is more electronegative than iodide. So you would think it can handle the negative charge better, but the atomic size is not the same. Fluoride is a very small ion. Iodide is a massive ion. It's huge relative to fluoride. So because iodide is so big, it can better handle the negative charge in fluoride due to its large size. That negative charge is spread across a greater area in iodide compared to fluoride. So bigger ions, well, bigger atoms can stabilize a charge better than smaller atoms because that charge is spread out over a large volume. You can think of it as it's diluted over a larger amount of space. Here, the charge is more concentrated in a smaller region, making it less stable. By the way, before we move on to the next topic, for those of you who are studying for the first exam in Organic Chemistry 1, feel free to check the links in the description section below. I have a video that can help you prepare for that first exam. The full version has about 90 questions, and it does cover acids and bases in the form of a test format, so feel free to take a look at that when you get a chance. Now let's talk about alcohols. We're going to cover the pKa of the OH group. Now water is not an alcohol, but it does have the OH group. And so the pKa of water and methanol are actually quite similar. The difference is the methyl group has been replaced with a hydrogen. After ethanol, we do have cyclohexanol, and terbutanol. Now the pKa for methanol is 15.5. For water, it's 15.7, and for ethanol, 15.9. Now there's also another one that I want to add to this list, and it's similar to cyclohexanol, but it's called phenol. Its pKa is much lower than a typical alcohol. The pKa is about 10. The reason for that has to do with the stability of the conjugate base. When you take away the hydrogen and you put a negative charge on the oxygen, that negative charge can delocalize into the ring, and it could be spread among 3 other carbon atoms. So because we have electron delocalization, phenol is much more acidic than any typical regular alcohol. Now, cyclohexanol, a secondary alcohol, the pKa is around 16 to 17. Terbutanol, a tertiary alcohol, the pKa is around 18. Now, the protonated form of methanol is much more acidic. Whenever you add an extra hydrogen, it becomes very acidic. This is negative 2.5. It's a strong acid. H3O plus, that's a strong acid as well. The pKa for that, negative 1.7. And for the protonated form of ethanol, it's around negative 2.4. So when you have an alcohol, if there's no electron delocalization, as in the case of phenol, the pKa is typically around 16 to 18 if you see an OH group. Now, if you have a protonated alcohol, the pKa is typically around negative 2. If you have a protonated ether, which is very similar to a protonated alcohol, the only difference is one of the hydrogen atoms was replaced with an R group, but nevertheless we still have an OH where the oxygen has a positive charge. The pKa is around -3. So as you can see, these two are very similar. Whenever oxygen has a positive charge and there's a hydrogen to it, the pKa will be around -2 or -3. For those of you who want to access the full-length version of this video, see the links in the description section below this video. You can access it on my Patreon page, patreon.com/mathsciencetutor, or you can join my YouTube channel membership program to get those videos as well. So feel free to take a look at that when you get a chance. Now let's move on to the amines. So let's look at ammonia, methylamine, diisopropylamine, and also we'll look at pyridine. So what do you think the pKa is for an amine? For ammonia, it's around 36. For methylamine, it's around 40, which is similar to ethylamine. Now isopropylamine, it's close to ammonia, that's 36, and the same is true for pyridine, at least according to my textbook. So the pKa for an NH group, where the nitrogen is neutral, on average, that's going to be somewhere between 36 and 40. Now what happens if we put a positive charge on the nitrogen? So let's look at ammonium, NH4+, methylammonium, CH3NH3+. Ammonium has a pKa of around 9.5, 9.6 in that area. Methylammonium, I've seen some sources say 10.5, others 10.7, so close to 10.6. And then the ethyl ammonium group, that's around 11. And then if you put it on a cyclohexane ring, it's going to be about the same, around 11. So for protonated amines, when you add a hydrogen to them and the nitrogen carries a plus charge, the pKa for that, it's going to be around 9 to 11. Now notice the difference between cyclohexanol and phenol early in the video. Cyclohexanol had a pKa of around 16 to 17. Phenol was 10. So when we add aromatics to it, or like when it's attached to an aromatic ring, the pKa will typically go down. The same is true for these two structures. So when adding a plus charge, we see that the pKa drops dramatically. But when adding an aromatic ring, it will also decrease as well. So the pKa for this, for cyclohexylammonium, that's around 11. But with a benzene ring, it's going to be less. It's 4 to 5. And even if you were to see this structure where the nitrogen is part of the benzene ring, the pKa is still around the same. It's around 4 to 5. Closer to 5 though. Now let's compare pyridine, which notice that it doesn't have a plus charge. It's in the 36 to 40 range, with pyrrole. So pyrrole looks just like pyridine. The only difference is it's part of an aromatic system. And typically when you add aromatics to it, the pKa will decrease. The pKa of pyrrole is around 17, much less than 36. So whenever you see an aromatic system and you're dealing with an acid-base question, generally speaking, the hydrogen that's associated with the aromatic system will generally have a lower pKa. And here's another example. This is the imidazole functional group. It's found in the amino acid histidine. Most amino acids have 2 pKa values, but some has 3. In the case of histidine, this one has 3 pKa values. The nitrogen on the left has a positive charge. It has 4 bonds. The nitrogen on the right has 3 bonds in a lone pair. But we know that when nitrogen has a positive charge, it's going to be more acidic. So in this structure, not only does the nitrogen have a positive charge, but it's also part of an aromatic system. So the combined effects of these two will decrease the pKa, as we saw in this example. So for this hydrogen in the imidazole system, the pKa is around 6 to 7. Not as low as this one, but still much lower than the other protonated amines. Now let's move on to carboxylic acids. Let's compare acetic acid with ethanol. So that's ethanol, and this is acetic acid. What's going to happen to the pKa of the OH group when we introduce the carbonyl functional group? The pKa of ethanol is 15.9, but for acetic acid, it's around 4.75, 4.76 in that area. As you could see, it's much more acidic. Now, if we were to add an amino group to the alpha hydrogen, the combination of a carboxylic acid and an amine is an amino acid. So this is one of the simplest amino acids, known as glycine. The pKa of the OH group is 2.3 for glycine. And we know for a typical ammonium group it's around 9 to 11, but for this one it's about 9.9. And the pKa of a peroxy acid, very similar to a carboxylic acid, but it's a little different. The OH is attached to an oxygen as opposed to a carbonyl group. It's going to be a little bit higher, so it's around 8. But notice the effect that this electronegative nitrogen atom has on the pKa of the carboxylic acid. By adding this electronegative group, the pKa dropped from 4.75 to 2.3. This is due to the inductive effect. Here's some other examples on it. By the way, the pKa for formic acid, for those of you who might be interested in it, so instead of a methyl group here, we have a hydrogen. The pKa for that is 3.8. So here we have acetic acid, and we're going to have the same thing, but we're going to add a bromine atom instead. Next, we're going to add a chlorine atom, and we're going to see the effect that it will have on the pKa of the carboxylic acid. So for acetic acid, we know it's around 4.75. With the bromine attached to it at that spot, it's around 2.9. With the chlorine atom, it's 2.8. With the fluorine, it's 2.6, 2.7. So by adding an electronegative atom notice that the pKa, it dropped in the 2 to 3 range. This is due to something known as the inductive effect. When you add an electron withdrawn group, what's going to happen is it's going to pull electrons through the sigma bond away from the acid. This has the effect of stabilizing the conjugate base. If you remove the hydrogen, you're going to get a negative charge. The more negative that negative charge is, the less stable the base will be. So if we can pull some of those electrons away from that negative charge, it will be less negative, more neutral. So this will be a weaker conjugate base, which leads to a stronger acid. So electron withdrawn groups, because they pull electron density through the sigma bond, they stabilize the conjugate base, making it weaker, thus increasing the acid strength and lowering the pKa value.